All right, we've reached a point now, having talked about efficiency and a bunch of different kinds of energy and so on. We need to talk a little bit more about conservation of energy and how energy can be transferred and is transferred in many sorts of circumstances, and sort of the results of that. Um, Basically, as energy is transferred and converted from one form into another, um, the laws of physics, as we understand them, say that energy is always conserved, which means the energy at the end of a process has to equal the energy that there was at the beginning of the process. But there's also this thing called the second law of thermodynamics, and that says basically involves entropy. And the idea of entropy is that the useful amount of energy is decreasing. So the total amount of energy stays the same, but the amount of energy that is useful to us is decreasing. Another way of saying that is that energy is dissipating. It's getting more spread out. It's getting more diffused. It's getting spread out more into the environment and less concentrated, I guess. So energy is most useful when it's concentrated, like in clumps. Um, so that it can be used. Like, I mean, energy in food, for example, is nice and concentrated. We can eat that, and then our bodies can use it. We can do stuff with it. So, the idea is that the amount of useful energy is being used up, being dissipated, spread out into the environment. All right? An example would be like these space heaters. Electrical energy goes into these things, and it causes them to heat up inside. That hot element inside then heats up the air around it, and then that hot air can be spread out into the room, um, and warm up the room at least a little bit. But with all of that spreading out, right, the concentrated heat, this is really hot in here, but the air around it is not really necessarily that hot. And you get far enough away and you can't hardly even tell the difference. So the energy is spread out into the room. It's also converted into forms that we're not interested in. Perhaps this thing makes some sound, some clicks. Maybe it's like heating and expanding, and it makes a few little sounds as it's working. That's not useful to the heating of the room. It's also emitting light. You can see that. That light is not useful for the heating. So there are extra forms of energy that are being converted here that are not really what we're going for in terms of heating the room. So that's an idea of where what we're going for is the heat, but what we're getting is all kinds of other things that are not really useful for heating the room. So that means that this heater is probably not very efficient. All right. So whenever we try to do something, or anytime an event occurs that uses energy, the total amount of energy remains constant. But of course, that's the principle of conservation of energy, right? Which we were just talking about. But it's changed into different forms, and not all of it is useful. So anytime you swing a golf club, for example, this guy, he starts with the club back here. This is the end of his swing. But he would start with it back over his shoulder. The club comes down like this. The ball is sitting there. He hits the ball with the club head, and then the club continues on. The useful energy to us is what happens to the ball as it flies down this way. So some of the energy is transferred to the ball, some of it is transferred into his muscles, which then heat up, and that's lost energy due to, basically friction or internal heating. Some of the energy stays with the club, and then is absorbed by his body as he spins around, again, resulting in some internal heating of the muscles to stop the motion of the club once it's hit the ball. Um, so there's a lot of wasted energy in there, that basically results in a very small increase in the temperature of his body and the air around him, and that's not useful to anybody, really. Um, Only a small amount of the energy, well, not a small, but only a portion of the energy goes into the golf ball, which is the whole goal of the whole swing. So there's a lot of energy transfer going on here as well that does not involve making the ball go, but all of that energy is needed in order to accomplish the goal of making the ball fly through the air. So um, anyway, the useful energy in this case, what we're going for is the ball flying down the course, and you get all this other stuff that's happening as well, which is not useful for that. So that's, again, that goes to efficiency. How much of the energy actually went into the ball? So pretty much nothing is ever 100% efficient at doing its intended purpose. Energy is always changed into some kind of useless forms and dissipated, spread out, dissipated to the environment. It's spread out into more sources, right? Say for a car, for example, the energy initially is in the fuel, and that's it. There's fuel in this car, and that's where all of the energy is coming from for operating this thing. That gasoline, basically, or whatever it is that's in there. Probably gasoline, high octane gasoline. So that burns. The gasoline burns. It releases the energy that causes the pistons and so on to fly around, and the pistons moving is what causes the motion of the tires and all of that stuff. Perhaps air conditioning is occurring as a result of the stuff going on in the engine and so on and so forth. And then you're driving. There's going to be friction between the tires and the ground. That's going to use energy. There's drag with the air. That's air resistance. So basically friction and drag. Sorry, friction and air resistance. Friction with the tires, air resistance with the air. Both of those together are called drag on the car because they're providing a force backwards when the car is trying to go forwards. So there's all kinds of stuff going on in here. The engine is heating up in a way that's not necessary, really, for producing the motion. I mean, if you could produce all of the combustion and everything without heating up the engine block, you would be more efficient. But of course you can't. You have to. There's no way to avoid heating up the engine block, really. But that heating of the engine block is not helpful to us, so that's wasted energy. There's all kinds of energy that's being wasted in pretty much everything we do. So the more you can minimize the waste, the more efficient you are. But anyway, so here's a transfer of energy where you start with chemical energy in the fuel. It gets converted to heat energy in the engine, which results in the motion of the pistons. The motion of the pistons gets transferred to the wheels. The wheels spin, and due to friction with the ground, they're able to propel the car forward, resulting in increased air resistance as the car goes faster and faster. So that's energy loss. More and more thrust is needed to overcome more and more air resistance to go faster and faster. So there's lots of energy transfers going on here. Alright, so we've been talking about a bunch of different ways that energy is transferred, and there are many processes that have several steps involved in the emission of energy, which we just saw several examples where it might take 3 or 4 or 5 or even more steps of transfer of energy before you get to the thing that you're trying to accomplish. So I just want you guys to be aware of those sorts of multiple step processes because they often ask questions about those kinds of things on the IG tests. Another example, in the universe overall, there are many stars, and those stars produce most of the energy that exists in the universe. Most of the energy on Earth comes from our sun. The sun is constantly producing immense amounts of energy in its core, and that energy is transferred out to the outer edges called the corona of the sun, and then that comes hurtling out into space, and a small amount of the energy produced by the sun hits Earth. And then Earth is able to be warmed by that, and it causes our weather, and it causes all kinds of interesting things. Solar panels can take advantage of it. Solar heating things can take advantage of it. It warms up the Earth. It produces photosynthesis so that plants can grow, and then plants produce energy, and then animals eat that. We eat the plants, we eat the animals, so on and so forth. All of that energy originated with the sun. So, and huge amounts of transfers, like tons of different transfers before that ends up in our bodies. So, and then we use it to do things. So anyway, I'm just hoping that what you got out of this video is that, one, the principle of conservation of energy is one of the major cornerstones of modern physics as it is right now. Energy is neither created nor destroyed, just changed in form. But there is a lot of transfers of energy that can occur in any given process. And almost always that energy becomes more spread out and less concentrated. So here we have an extremely concentrated amount of energy in our sun. But every second, a lot of that energy is being spread out into the surroundings, all throughout the solar system. So pretty much any event where energy is used causes that energy to become more spread out, more dissipated, less useful. So, all right. hopefully you found this video interesting and helpful, and talk to you next time.